Okay, so today we start our final unit, Unit 5. Some of you may still be working on the Unit 4 test, which is fine. You do have extra time for that if you need it. I have some of them in. I was holding them until I got more of them in so I could grade them at once. I'm more consistent if I grade them in one stretch. So I'll have those back to you. Hopefully I'll have most of them back to you by Wednesday. I should have them in today or tomorrow. This last unit, we only have about 4 hours of lecture. Our next test is going to be on Wednesday. That would be May 17th. So that's next week, Wednesday. So we only have 4 hours of lecture for this section of the course. Doing the test on Wednesday just to make sure everybody has time to finish. This last test, I try to write it a little bit easier so you don't need to don't need as much time for corrections and stuff like that. You will still be able to correct that test and turn it back in. Then that final day, May 19th, will be our final day. There will be some extra credit problems and opportunities that day, and I will answer any questions on that test for people that have corrections to do that have questions on test 5. So anyway, section 5 here, Unit 5. Is on statistics. And in 4 hours, we can only do a very brief introduction to statistics. We could really go on for 2 whole semesters on this topic if we wanted to. And in fact, for anybody who's an underclassman who is interested, WITC does offer a probability and statistics course over this same network. So if it's something you're interested in, talk to your guidance counselor. Statistics has a very bad reputation academically as being an extremely difficult course. And it can be a difficult course for a couple of reasons. One is vocabulary. Statistics is almost a foreign language. We're taking words that you've heard before and have used every day, and we're using those words for very specific meanings, for very specific things. So their definitions, their usage might be slightly different than what you've used them for in everyday life. So we need to make sure we get some of the vocabulary down. The other thing is that it's a very strict application of probability. So to really understand statistics requires a little bit of a background in probability. And in this class, for the next 4 hours here, we're not going to have a lot of time to get into probabilities. So we're going to do kind of a cursory view of it. In a longer class, you'd have to make sure you understood probability. And then the other thing is there's a little part of statistics that kind of contradicts common sense, because it's not black and white. There's gray areas. And those gray areas can never be totally eliminated. So we try to set parameters to limit their impact. And like I said, we're not going to get into a lot of this. We're going to do mostly vocabulary and summarizing data for this class. But the probability and the gray areas, decision making, are big. There are 2 main areas of statistics. First one is what we call descriptive statistics. In descriptive statistics, we are concerned with gathering, summarizing, and displaying data, information. Data is nothing more than information gathered about a group. And that's mostly what we're going to be concerned with in this section, this little unit of this class is descriptive statistics. The next step would be something called inferential statistics. And inferential statistics is that next step of making the data useful. So inferential statistics is using that information, mostly from those descriptive statistics, to make decisions. Now those decisions might be a prediction, they might be a conclusion about about something that we can't totally see. Or it could be just making a big decision based on those numbers, those statistics. So with all this said, statistics, it's always classified as a math course and a math topic. And it uses math, but it really isn't necessarily a math topic. Statistics uses math, uses calculation, uses numbers, but it's more about organization and decision making and almost a logic type. But it's not a direct logic because you have evidence-based decision making. It's not always, as I said, black and white. So more vocabulary to deal with on our descriptive statistics. The first big thing we have to understand is something called a population. And a population is a group that we want to learn about. Now that group could be people, it could be parts off an assembly line, could be treatments for a certain illness. The population is something we want, the item we want to learn about. And the population can sometimes be difficult to define. For example, if I wanted to conduct a survey to see who is going to win the next major election, so we're going to do a survey to try to predict the next election winner. Doesn't matter whether it's President of the United States or city mayor. We want to predict an election. Well, our population there is not the candidates. We want to learn about who's going to win, but who's going to win is not necessarily determined by the candidates. What we're really trying to learn about there is voters. So let's say we're doing a survey to try to predict who's going to win the next mayoral election in your city. Well, the population is not all voters in the city because some of them won't vote in the election. So what our population here really is all voters who will vote in the next election. And once we've identified the population, here we define the population, it's going to still be tough to figure out who's really in the population. Because in this case, there might be some people that aren't sure yet whether they're going to vote in that next election or not. Some of them might not decide till the day of, oh, I've got time, maybe I'll go vote. Or I'm busy, I'll pass this time and not worry about it. So, I mean, it can be, the population itself may be almost impossible to identify. Now, with that population, we have a process called a census. And a census, the United States does a census every 10 years. So coming up in 2020, we will start another census process. They're trying to gather information about every household in the United States. A census is trying to gather information from a whole population. So back to our example of the mayoral election, you would try to identify every voter who's going to vote in the next election and gather information from every one of them as to who they're going to vote for, which should give you a pretty good prediction. Now, of course, it won't be absolute because some people might change. Some things might happen that changes a voter's mind, or somebody might not necessarily be totally honest. That's something we can't control. Now, there's something called a parameter. A parameter is a piece of information, a piece of data that describes the population. So if we were to actually get information from, to actually be able to identify every voter who's going to vote in that next election and find out who they plan to vote for, and we were able to say 58% of voters plan to vote for this candidate, that would be a parameter. We're describing the whole population. Now, even if we didn't get everybody, we might say that we believe about 58% of voters are going to vote. Even though it's an approximation and it wasn't necessarily gathered from everybody in the population, we are still using it to describe the population. So it would still be considered a parameter. Now, smaller than a population, we have something called a sample. And a sample is a subgroup of the population. Now, we're going to talk a lot more about the sample coming up here in a couple minutes. But let's define some other vocabulary related to samples here first. A survey is an attempt to gather information about a sample or from a sample. So we've selected this smaller group of the population that we're going to gather our information from. And so gathering information from them would be referred to as a survey. And then, of course, the big word of the day is a statistic. A statistic is that information, a piece of information describing a sample. We might say that out of 210 people surveyed, 116 say they're going to vote for this candidate. That is a statistic. It comes from our sample. So let's talk about that sample more. Because in the beginning level of statistics, there's a lot of important concepts relating to this sample and samples in general. Two things about samples is we must have a good sample, and that's called a representative sample. A representative sample is a sample that closely represents the population. Well, what does that mean? Well, for example, if 60% of the voters in the population plan to vote for this candidate, there better be close to 60% of the voters in the sample that plan to vote for that candidate. They better be really close, and its characteristics better be, its statistics of the sample better be close to the population parameters. To create a representative sample, we're trying to avoid something called sample bias. Sample or sampling bias. And what that is just the opposite of that. That's the difference between a sample statistic and a population parameter. Now, we can't expect to totally eliminate sample bias. We can't expect our sample to perfectly represent the whole population, because it's just not very likely that it will. So we talk about sample bias and representative samples. The representative samples, we're trying to minimize sample bias. And then when we get into the inferential side of statistics, trying to decide, okay, estimate what would be the possible estimated size of the sample bias, then account for that in our decision. For example, let's say we estimate that the percent of people that we get from our sample might be plus or minus 10%. So if we survey our sample and we find that 52% are in favor of something, well, what that's telling us is that could be anywhere from 42 to 62%, which means we really can't draw a decision either way, because there could be less than half the people or more than half the people that are in favor of that. On the other side, let's say that we say that estimated sample bias is plus or minus 10%, and we do a survey and we get 65% that are in favor. Well, now we can say that pretty confidently that we think that the whole population that this is going to be voted in favor of, because even with that plus or minus 10%, we're still looking at, from the 65 going a range of 55 to 75%, which either way, no matter where it is in that range, it's still above that 50% mark, above the halfway point. So that's a big part of the inferential statistics. Like I said, we're not going to get in that for this course, is estimating that sample bias and accounting for it. How far do we have to be past our mark before we can say sample bias is not going to affect our decision anymore? So how do we minimize sampling bias? How do we draw a good sample? Well, there are two major considerations. The first one is sample size. Now, for this course, sample size is represented by the small letter n. I'm going to put sample in front of that. If we were talking about population size, I'm just going to do a little side note here. Population size is represented by the capital letter N in most textbooks. Our sample size must be large enough. Typically, it is not large enough. If you wanted to figure out, what that result of that election is going to be, if you just surveyed 10 people and found that 6 out of 10 people were going to vote in favor of that person or that candidate, well, you can't say that we estimate 60% are going to vote for him, because that's too small of a sample. If you have a city of 2,000 people, 10 people is not going to be enough to represent everybody. It is possible to have a sample that's too large. Statistically, the problem is if you get a sample, and usually they say either 5, 10, or 20% of the population for too large, depending on what type of statistical process you're doing. Let's say 20% is what we're looking at. The reason they're saying that sample might be too large is if you can sample 20% of the population, well, then it's not that much further to go to get information from the whole population. So, kind of a stretch there, not as big of a deal to have too large of a sample, but it still can be a consideration. So sample size. We're not going to talk about finding sample size in here, determining sample size. One general rule of thumb is that your sample size should be greater than or equal to 30. And the only reason that comes in is it actually has to do with probability. If your sample size is smaller, and there are a lot of things you can do with a sample size smaller than 30. But if it's smaller than 30, you have to know a little bit about the population so that you know what type of probability to use on it. If it's bigger than 30, then there's something called normal probability that will always be applicable and we could always use. Again, not going to be a consideration in this course because we're not doing inferential statistics. Another part of a good sample is a good sample must be randomly selected. Again, if we're looking at figuring out who is going to win that election or the result of that election, that vote, you can't just walk around your block and ask questions of everybody who lives on your block. That's not going to work. Because they live in your neighborhood, there might be special things going on in your neighborhood or something in your neighborhood that influences them on an issue. So randomly selected, what that means, sorry, it took me a second to figure out you're just trying to open the window there. Thought you were trying to escape for a second. Randomly selected just means that every member of the population has an equal chance of being selected. So again, if you're walking and just walking around your block asking your neighbors, people that live more than a block away from you have no chance of being in that sample. So that's not a truly random sample. Again, if this were a fuller course, we would spend a little bit more time talking about different sampling methods and ones that are acceptable and ones that are not. Because of our time restrictions, we're not going to deal with that. But just be aware that you have to be careful how you select that sample. The best way to select a sample is just the old, putting names in a hat. Now that sounds kind of, corny, but really if you could take the names of everybody in the city, every registered voter in the city, or everybody in your population, put them in a hat and draw out the ones that are going to be in your sample. Mix them up good and draw them out. That is still the best way to draw a sample. And that's actually something special called simple random. Simple random is actually a little bit stronger than just random, because not only does every person or every item in the population have an equal chance, every possible group of the size that we're sampling has an equal chance. So it's the best way to do a sample technique. There are cases where random but not simple random are acceptable. Those are called samples of convenience, where we have another mechanism that makes it a little bit quicker, easier to draw our sample. Again, that's more than what we have time for in this course. So next we want to talk about data, the data. We're not going to get into a lot of talk about random variables and stuff like that. But what we are doing in these surveys, we are asking a question. So when I say survey, I'm using that as kind of a broad term, survey or experiment or whatever. There's a question that's being asked. And the answer to that question is our data. So the question might be, what's your favorite color? Well, your answer, whatever color you name off, is a piece of data. It might be, how tall are you? We'll measure you and your height. That's a piece of data. That's an answer to that question. The question might be, we might be talking about a medical drug treatment. Does this drug work more effectively than another? Well, again, that's not a very good question. We have to define that question, something that we can measure. So let's say we're looking at a drug to treat HIV. Does this medication significantly lower the white blood cell count in the bloodstream? Yes or no. So, that's a piece of data for each individual. Whether it's effective or not is a piece of data. So that question we ask produces our random variable, produces our data. That data can be either what's sometimes called qualitative, by some textbooks. Other textbooks just call it categorical, which I think is a better term because it's more descriptive of what it really is. And in a categorical or qualitative data, the answer to that question puts each item into a category. So for example, if I asked you, what is your favorite color? And the color you answered puts you into a category. Whether it's red, blue, green, purple, whatever, it puts you into a category of people who choose that as your favorite color. Every yes or no question is categorical. You know, do you favor this candidate, or do you favor this policy? That's a yes or no question. It puts you into a category, for or against. Who will you vote for in the next election puts you into categories. Those are all categorical pieces of data. The next one is sometimes called quantitative. Quantitative comes from your result is a quantity, or again, I prefer the term numerical. The answer to that question is a number. Now, there are two different types of number, two main types of numbers we can get into here. We could have what's called discrete numerical data. And in discrete data, the number is found by counting. That might be how many cars you own. You count 0, 1, 2, 3. How many children you have. You know, again, you'd count 0, 1, 2, 3. You're going to count them to come up with that number. The other is called continuous. Continuous data, the number is found by measurement. Now, there are a lot of other definitions for discrete and continuous. One of them is, you know, for discrete, they say there's gaps in between. Like for children, you can't have 2.5 children. You either have 2 or 3. So there's gaps in between those numbers that cannot be possible. For continuous, they say there's always numbers in between. So let's say you are 5'3" and 7/16 inches, and your friend is 5'3.5" or 8/16 inches. Even though you're only a 1/16 of an inch apart, there's always possibility that you can find somebody that's in between your heights. Continuous data is always going to be rounded. We must determine what's going to be our smallest degree of precision. How far are we going to, where are we going to round it off? So sometimes continuous data looks like it has gaps in between, but that's only because we've chosen to only measure it down to a certain degree of precision, down to a certain level of measurement. Now, there's two of them that are always big arguments. One of them is money. Is money discrete or continuous? Well, because we can calculate interest down to the 100th or 1,000th of a cent. But when it comes to reporting money, money is always reported to the nearest penny, down to the nearest cent. So even though it can be calculated to smaller units, money is discrete in my book because you are counting pennies. It can still be counted. The other one is age. Age can be tough because age kind of depends on how you define it. If you're asking a person their age, and you're defining their age by how many birthdays they have had, well, that is something they can count. That is a discrete variable, number of birthdays. If you're describing age or defining age to be how long have you been alive, well, you could measure that down to the nearest second, or you could measure it down to the nearest tenth of a second or hundredth of a second. No matter how precisely you measure it, it is possible to take it out to more decimal places, to measure it more precisely. So that would be continuous if you're defining age in that terms, is how long you've been alive. So many times it depends on how exactly you define your variable, whether it's discrete or continuous. So from there, there are levels of measurement within each that we're not going to talk about. Nominal, ordinal, all that good stuff. We're going to move on now to organizing data. And the biggest thing is, how do we organize data and why do we organize data? Well, our data comes in a few different forms. We're going to start out with raw data. And raw data is nothing more than a list of responses to that question, a list of the answers to the question we asked. So let's say that we are talking about favorite color again. And I give you choices. We're going to limit our choices here to red, blue, or green. So I'm not necessarily asking for your favorite color. I'm asking, of those three colors, what would you prefer? And to save time, I'm just going to create some responses here. So let's say that our responses we get are red, red, blue, red, green, blue, green, green, red, green, blue, red, blue. Let's see how many have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's go with that. Red, green, red, red, blue, green, green, red, green, blue, blue, green, blue. And let's keep going here. Red, red, green, blue, green, green, blue, blue, green, blue, green, red, blue, blue, blue. And I'll put one more on the end here. Let's go with green. So we got an even 40. So there's our 40 responses that we got. Well, looking at that, can anybody tell me which one occurred the most? I mean, 40 is not a large number of responses, but looking at it, it is really hard to look at that and decide, you know, one of them is the most popular. Human psychology and statistics does actually use a lot of psychology in its organization and stuff. Human psychology, the human brain is typically capable of considering between 7 and 13 items at one time. Tries to view more than that, some of them fade out. So if we're looking at this, if we're looking in this area here, it looks to be very apparent that red seems to be the most popular color, because red is very prominent there. If I'm looking at this area right here, you'd be tempted to say green is the more popular color because green is very prominent there. But if you're looking over here, you might want to say blue is the more prominent color, more popular color, because blue is definitely dominating that section of the data. So displaying raw data is really tough to interpret. So we tend to take the next step, which is to organize it into tables. The most common table is something called a frequency table. And a frequency table lists out all the possible responses. For example, here we might have, well, we're going to do the colors as our possible response. And we were limited to red, blue, and green. And then we list the frequency. Now I left a space here. Normally on a frequency table, those are the only two columns we would have displayed. But since I am working on creating this table, I'm going to create a third column in the middle here for a tally. So I'm just going to go up here and look at this and say, okay, I've got red, red, blue, red. So I'm going to tally red, red, blue, red. Green, blue, green, green. So green, blue, green, green. Red, green, blue, red, blue. So red, green, blue, red, blue. Pretty close so far. Red, green, red, red. Red, green, red, red. Blue, green, green, red. Blue, green, green, red. Green, blue, blue, green, blue. So green, blue, blue, green, blue. Again, pretty close so far. Red, red, green, green, blue. Red, red, green, green, blue. Blue, green, blue, green. Blue, green, blue, green. Red, blue, 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 green. So red, blue, 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 green. So our frequency here, red is 12, blue and green are both 14. Now looking at that raw data, I'm guessing that very few, if not any of you, would have guessed it was going to be that close. Now to clean up this data table, the frequency table here, we would arrange it like this. Removing that tally column because we don't need it anymore. It was a working column to help us create it. So the clean frequency table would be this one right here. Now there are more things we can add to that frequency table. Depending on how we're going to analyze the data, we might want to add something called a relative frequency. A relative frequency is what proportion of the time it occurs, what rate of the time. And to do that, you'd have to first find a total. Well, I add those all up and I get 40. So the relative frequency is just each raw frequency. It's not labeled like that, but this is the raw frequency divided by the total. So 12 divided by 40 is 0.3. 14 divided by 40 is 0.35. 14 divided by 40 is again 0.35. So those are our relative frequencies. Those better add up to a total of about 1.00. Now again, 40 is a pretty easy total to divide by. If it had been like 30 even, or 60 or 70, numbers that when you divide by them, you might get continuing decimals. We would have to round off that relative frequency, and it might come out to be 0.999 or 1.001 or something really close to 1, but it better be close to 1. And we could also have something called percent frequency, which is really nothing different than the relative frequency. We're just expressing it as a percent instead of a rate. So 0.3 would be 30%, 0.35 is 35%, and again 35%. And again, something we better get a total that are really close to 100%. 99.9 or 100 and 100.1 or something really close to exactly 100% total there. Okay, so that is organizing data in a table. Now here with only 3 categories, it isn't so tough to look at this and say, yeah, red occurs the least often and blue and green are tied for the most often. But if there were, 10 or 11 or more categories here, if I had given you more choices of color, with 10 or 11 categories there, it might be more difficult to look at it and quickly determine which one is the most chosen and which one's the least chosen. So that's where we move on to the next level of organizing and displaying, which is called a graph. Now I'm just going to show you one of the graphs, and on Wednesday we'll talk more about the types of graph used. One possible way of graphing this might look like this. Red, blue, and green. Numbering up the sides, I have to go to at least 14. So let's do 2, 4, 6, 8, 10, 12, and 14. Oops, I wrote 10 there. Notice I don't have to go up by ones. And so for red, went up to 12. Blue goes up to 14. Green goes up to 14. So now from this graph, you can very quickly just glance at it and see that red is the smallest one. It's the shortest bar. This is called a bar graph, by the way. We'll talk about that with our types of graphs on Wednesday. And we can see that blue and green appear to be very close, if not tied. If there were more categories, we had more colors over here, even with more bars, you could still very quickly tell which bar is the tallest, which one is the shortest, who had the most or the least. And that is one of the strengths of graphs, as you can usually very quickly tell which one is the least or the most. Also, if I were to say, hey, which was chosen more, blue or green? Well, here you can very quickly see they're about the same. And in this case, they're exactly the same. You can compare. Now, in this graph, since we have relatively low numbers for the frequencies, you can tell pretty much exactly that this is 14 and this is 12. But let's say that we had, instead of doing 40, we had done 400 people. Let's say this was 120 and 140 rather than 12 and 14. Now you'd look at that and say, well, is that 140 or is it 138 or 139? It would be difficult to get exact numbers. That's one of the weaknesses of a graph, is exact numbers. If you want exact numbers, that's where you would still go back to the table. And in the table, you can see exactly how many were chosen for each. Okay, it's about that time here. We're getting low on time, so I'm going to cut it off there. There is no homework for Wednesday. On Wednesday, we'll talk about graphing, and we'll get into more about creating the graphs, and there'll be homework on that. So you guys have a great day, and we'll see you on Wednesday.